Hello, today we are going to be talking about alkynes. Alkynes are anything with this functional group, carbon-carbon triple bonded. They've got some pretty interesting applications, both natural and synthetic, and I've got them listed here from my textbook on the right side of the screen. You can also see what all these compounds look like. Some of them are pretty complex. I think they look pretty cool. We can spot our alkynes here, here, there, here, there. So they often come conjugated, which means they're like one carbon apart from each other in nature. So if we're going to be naming alkynes, they're kind of in the middle / kind of low on the priority list. And when I say priority list, this is what I mean. If I have this compound, for example, then we are going to prioritize our alcohol because that comes higher on this little list we have than alkynes do. I mean, you don't have to memorize this list, but kind of know that things with oxygens tend to take priorities. So alcohols, carboxylic acids, esters tend to be higher up than things like alkenes and alkynes and alkyl halides. So if I'm going to number this compound, I'm going to say that my eraser's not working, apparently. No, I'm going to say this is number 1, this is 2, 3, 4, 5, 6. So this is going to end up being hex 4-ine 1-all. So it's 1-all because we're prioritizing the alcohol, and it's hex 4-ine because 4 is lower than 5, and so if the alkyne is on carbons 4 and 5, we're going to say 4 because we don't like higher numbers in IUPAC nomenclature. So the other thing you might notice about this drawing is it looks kind of weird. All these carbons are in a row instead of being all zigzaggy like we normally draw them. And that's because alkynes have a linear geometry. So if you remember our valence shell electron pair repulsion theory, that basically says electron pairs want to be far apart from each other, right? So if I have any alkyne, and these R's can be carbons or they can be hydrogens. Anyways, if we take one of these carbons, it's bonded to only 2 things, right? All of these electrons are in one group, and these are one group. So how far apart can we put 2 electron groups with an angle? 180 degrees is the most. So these alkynes are going to be linear, which is why you see them looking kind of weird in drawings. I've also seen people draw them just regularly, like this. But some professors might be a stickler about this, say this is incorrect. I suggest you kind of know how to label or draw the kind that I did at first. So that's how to name them. So for example, if I were to write this one here, oops, that doesn't work. If I were to write this one here, yes, I'm making it complicated. What are we going to name this one? Well, we're going to prioritize our alkyne over the alkyl halide. So it's going to go 1, 2, 3, 4, 5. So we're going to say that it is a 5-chloro, 6-phenyl, and here we're just doing alphabetical order. And it's pent 2-ine. Okay, so now you might have a sense of how they're named. So now we can continue on with reactions. So alkynes are relatively cheap to synthesize. You can make them out of coal. So here when it says coke and lime is just heated up coal. And you can do a few things to it, and you can make what we call acetylene. And acetylene always confused me because I was like, oh, it says ene, it's an alkene. But acetylene is an alkyne. So that is our simplest alkyne. And then you can usually build higher alkynes with acetylene, and we can talk about how that is later on. So alkynes are a unique group. They've got shorter bond length than other alkyl, like substituents or other carbon compounds because of the triple bond. So because there are so many electrons being kept in there, the nuclei are really attracted to those electrons, which makes them kind of attracted to each other. So this is going to be a shorter bond length than alkenes or alkanes. And when it says the A with a little circle over it, that's just angstroms. It's a unit to measure really short distances. You might see it in chemistry, you might see it in biology or biochemistry. Alkynes are also acids, but only if they're what we call terminal. So terminal means at the end, right? If you have a terminal illness, you're going to die. So if you have a terminal alkyne, it's the end of the alkyne, which means that that carbon is going to be bonded to one carbon, but also one hydrogen. So it's going to look something like this, where this is the terminus or end, right? You can also have a doubly terminal alkyne. And this is acetylene that we were talking about earlier, where you have two of these guys at the end. If it's not terminal, it doesn't have hydrogens, because remember, carbons in alkynes can only really be bonded to two things. So if you're an end, you have a hydrogen. If you're a middle, you've run out of things to bond to and you don't have a hydrogen. So they're acidic because that negative charge can kind of delocalize into all the bonds in the triple bond. And you can have two different ways to deprotonate an alkyne. We've got two kind of main reagents that we use. So one of these is called sodium amide. And this is NaNH2. So NH2 is amide with a negative charge. The sodium is positive, the amide is negative, right? This is not to get confused with sodium and ammonia, and you're going to see why I'm saying that later in the video. So these electrons can act like a base and grab this proton, and this electron pair can be left to our alkyne. And we can get a nice little negatively charged alkyne because we took away the proton. You can do basically the same thing with an organolithium reagent. And if you don't know about organolithium reagents, then you can watch my videos on organometallic reagents. So here is methyl lithium. And just as a review, organometallic reagents, we like to say the metal is positive, and then we like to pretend this bond doesn't really exist or that it's ionic. And then this carbon is negative, which is useful to us because it can act like a base here. And we can get our same type of product. And then on the side, we're going to get methane. And then the lithium can be positive and dissociate with the negative acetylide. We call it an acetylide. Even if it's not acetylene, it's like kind of its relative. So these are called acetylides when you have a terminal alkyne and you deprotonate it. So why the heck would you want to deprotonate a terminal alkyne? Well, they can be useful as nucleophiles. So if you're learning these things in the same order that I did, this is the first you're seeing of carbons as nucleophiles. And this is going to be really helpful for us because we can make new carbon-carbon bonds. Because so often when we've learned these nucleophilic substitution reactions, our carbons are partially positive, right? So that means that something partially negative is going to attack it and make a new bond. So if we can have a partial positive carbon, and then we can have this negative carbon, they can be attracted to each other, they can make a new bond. And voila, we can synthesize something or make something. So again, here's sodium amide, which, like I said, is something that can deprotonate a terminal alkyne. So we've got this negative charge, these extra electrons on the amide anion. They can grab this hydrogen, and these electrons can go to that carbon there. The arrow, that last one I drew, is pointing to the carbon, not to the bond, because we're having electrons, and they're being attracted to a nucleus. Okay, so this is going to get us what we just kind of saw, which is our acetylide, which has an extra electron pair and is negative. So there is our nucleophile. These guys, anything with a carbon that's negative is going to be a strong nucleophile, which means it's going to do what type of reaction? That's right, it's going to do SN2-like reactions because it is strong. So here's an example of an SN2-like reaction or an SN2 reaction. It's going to go and attack this carbon, which is partially positive. Our other clue to this is that this is a methyl carbon, right? It would make an awful cation, so this is definitely going to be substitution. And there's a bond in here I forgot to draw, and it's going to give its electrons to the iodine. And we're going to make a new bond, and here's our new carbon, and then we'll have iodine floating around as an anion somewhere. What we can also do with these nucleophiles is we can put them in with carbonyls, and maybe you've seen carbonyl chemistry before, maybe not, but what's going to happen is again an SN2-like reaction, but instead of having a leaving group like iodine that just leaves, our leaving group is going to be these electrons in the double bond of the carbonyl. So we're not going to get two things, we're going to get one gigantic thing. And it's going to have an O- because here we had 2 electron pairs. And here we're going to have 3. And so this was all the stuff that was over here. Now our last step is just to add on a proton, and we can make ourselves an alcohol. So that's how to use alkynes as nucleophiles, and then if we want, we can always add to them to make them alkanes, if that's the product we want. So we can also make alkynes, and we've seen elimination before. We've seen E1, we've seen E2. Here we're going to be focusing on E2 reactions. So there are some strong bases we can use, and we really need to use a strong base, and the reason why is we're not just doing one E2 reaction, we're doing 2 E2 reactions. Right, to get from an alkane to an alkyne, you need to go through an alkene. And if you have an alkene and you want to do an elimination reaction, it's harder than doing it from the alkane, so you're going to have to use a stronger base. Some examples of this are fused potassium hydroxide, so this is liquid potassium hydroxide, and sodium amide, again, our best friend in alkyne chemistry. So whatever this base is, I'm going to write base here. So this can be the amide anion, this can be the hydroxide anion. But this base is going to do what bases do, and it's going to grab a proton. And because it's grabbing the proton and not the electron pair that it's using as a bond, this bond is going to become our double bond. And this carbon here is going to say, I have too many bonds, what do? It's going to kick off our bromine. And we're going to get this here. And it really doesn't matter if it's like a cis or trans or E or Z isomer or what, because we're going to do this again. We're going to have another equivalent of our base, whatever that may be. It's going to grab another proton. We're going to make another bond, and we're going to lose another leaving group. And this is going to end us with an alkyne. So we can do that. We can also do it backwards. So we can add to alkynes and make alkanes. Or we can make alkenes if we know how to stop it. So we can halogenate it like we were dehalogenating up there, but backwards. Or we can hydrogenate it. So we're going to start with hydrogenation. So this is just if you don't want anything special on there. So this is often done with hydrogen gas and some type of metal catalyst. So it can be platinum, it can be palladium, it can be nickel. And when you do this, it's a super fast process. It's really reactive, and it's going to take you straight to the alkyne. 1, 2, 3, 4, 5 carbons. There. So that's what you would get. There is a way to stop it at the alkene, and this is called poisoning the catalyst. It's not as bad as it sounds, it's just slowing down the reaction enough that we can stop our reaction at the alkene level. And so the way that this works, the way that our catalytic surface is set up, is that if we put in our poison, which in this case is called Lindlar's catalyst, it's going to be whatever metal, along with something called quinoline. And this is going to make us a cis alkene. And that's just like the way things are arranged in space. It's going to end up like this. But don't worry, if we want a transalkene, there is a way to make one, but it's a different reaction. It's called the Birch reduction. So in the Birch reduction, we're going to have sodium and ammonia. This is, again, not to be confused with sodium amide. So you're going to see some type of separation between them. You're going to see a comma, you're going to see a slash, and it's not going to be an ionic compound, but rather two things just there. It's going to be sodium, metal, neutral, and ammonia, also neutral. And these two things, somehow, I do not know off the top of my head, check a textbook, they're going to make something called a solvated electron, which is just this little electron that hangs out all on its own because it doesn't know who to be with. And that electron is kind of going to propagate the reaction, I guess in the same way that like a free radical would propagate a reaction. And it's going to end up making a transalkene. So this one is going to look instead like that, as compared to the Lindlar's catalyst and making a cisalkene. So that's how to make specific alkenes and alkanes out of alkynes. You can also halogenate, like I mentioned before. So you can do this with a dihalogen. And in that one, you're just going to do the same thing you did for alkenes, except you're doing it twice. So if you want to know the mechanism to this, I'm pretty sure I made a video on alkenes. And in that, we talked about how the triple bond, or, well, in that case, it was the double bond, is going to act like a nucleophile. And London dispersion forces are going to make it so that one of these halogens is kind of positive at one point in time, and one of them is going to be kind of negative. We're going to end up with a bromonium ion in this case, because we're using bromine. It can be any like halonium ion for any halogen. It's going to look kind of like an epoxide, if you've heard of epoxide. It's going to be a little triangle. It's going to be very unstable because organic chemistry doesn't like triangles. And so eventually what that's going to do is it's going to separate out into a dihalogenated thing. So we're going to get something like this, and it's going to be some type of racemic mixture between cis and trans. And then, I mean, in this case it doesn't matter because there is no cis and trans with a terminal. Then we're going to get an alkane, and it's going to be a tetrahalogenated alkane because we added like an X2, a halogen 2, Br2, whatever you have, twice. You can also do a hydrohalogenation, which is where you take like HBr, HCl, HI, whatever it is, and add it on. And this is where our old friend Markovnikov comes into play. So remember that this mechanism, the nucleophilic addition, requires a carbocation. So where would make the better cation? Here or there? That's right, the first one, because it's secondary. Primary cations do not last for long. So the way that this mechanism goes, the special thing, whatever it is, the Br, the OH, the I, what have you, is going to go on the more stable cation carbon. So we're going to get something that looks like that. So we can also hydrate these alkynes. So again, this is going to be using the nucleophilic addition. We're going to be using Markovnikov's rule. But here what we're actually going to do is we're going to stop this at the alkene, and we can do that depending on when we stop our reaction. And so it's going to look like this. And all the sulfuric acid is a catalyst, and please again go back to the alkenes video because a lot of these are repeat reactions with those, because you're doing essentially the same thing. You're taking a double bond and using it like a nucleophile. But in any case, we're going to get something that is called an enol. And the reason it's called an enol is here is our ene, and here is our ol, right? Ene is alkene, and ol is alcohol. And this can do something kind of cool. It's called tautomerization. So tautomerization just means that we're going to be replacing one hydrogen somewhere else in the compound. So it's like an isomer, but we've displaced one hydrogen. So the way that this works is it can be acid or base catalyzed. I'm going to show you the base catalyzed way. So this base is going to do what bases do. It's going to take a proton. It's going to leave its electrons with this oxygen. And this is a reversible process, so I'm going to be drawing equilibrium arrows. It's going to be in equilibrium with this form where the oxygen has an extra electron pair and is negative. So this oxygen is going to do what we've seen oxygens do before with negative charge, and it's going to make a carbonyl group, and this is going to push out electrons from this double bond. So we're going to get this negative carbon now, and this base, which is now its conjugate acid, it has a hydrogen on it, is going to donate that hydrogen. So actually this is going to take the hydrogen and give the electrons back to the base. Because remember, if it's catalyzed by the base, then it has to be like regenerated at the end, as catalysts are. And we're going to end up getting what we call the keto form, because it's a ketone. These can also be aldehydes, and that's a bit misleading, but this is keto-enol tautomerization. So we can take an alkyne, we can hydrate it, and then we can use keto-enol tautomerization to make it into a ketone. So there's also another way that we can do this, and the reason I bring up this other way is because the mechanism I just showed you, or like the reaction I just showed you, is Markovnikov, right? So this carbon here made the better cation, so that's why we put the OH on it. It was acid catalyzed, it involved a cation. The other way that we can do it, it's anti-Markovnikov, and you don't have to know the mechanism for it, probably not, I hope not. But it's going to be using this thing called Cia2BH. Cia is not the writer of Chandelier. Cia is sec-iso-amyl, and amyl meaning pentyl. People used to use that in like old chemistry language. Don't ask me why, but this is what it looks like here. And so that is going to be attached to boron and a hydrogen. So remember back in our alkenes unit, we talked about hydroboration and how that was going to do anti-Markovnikov addition. Well, this is going to do kind of the same thing. It's going to do anti-Markovnikov addition, and it's going to make us this version, which looked different than the other one, and we can do keto-enol tautomerization on this one, which I don't have room to show the mechanism for, and that's going to end up being like this. And that's kind of what I meant when I said that the keto form can be an aldehyde. We can also do oxidation. So this is going to turn our alkyne into some form of something with an oxygen, as the name would suggest. So it can be like a ketone, or it can be a carboxylic acid. Usually you're not going to see an aldehyde because things that can make aldehydes can oxidize further into carboxylic acids. So it's either going to be ketone or an acid. So if you use potassium permanganate or KMNO4 and you don't use any type of heat, what you're going to get is one product, and the one product is going to have two different carbonyl groups. And if it's like a terminal alkyne, it's going to have an acid at the end too. If you use heat, or if you use something called ozonolysis, and this here is ozone, so ozonolysis, ozonolysis, lysis is breaking, so this stuff, these two reactions are going to break your reactant down into two pieces, and these two pieces are going to be carboxylic acids because like they are end pieces by nature because you broke it in half. So I've seen retrosynthetic analysis problems, which means that like you're working backwards, and they'll give you these carboxylic acids and they'll ask you, okay, which alkyne did they come from? So then all you have to do is treat every carboxylic acid like it's supposed to fuse with another one and make an alkyne, working backwards. So that's basically all the reactions that you have to know for alkynes. Here's a little schematic of all of them, so you can screenshot this and use this to kind of study them all. I hope this helped.